Hello everyone, I am Siba Smarak Panigrahi. Along with me will be Sohan Patnaik. We are students of Indian Institute of Technology, Kharagpur, India. This is a poster on the reproducibility work of the paper value alignment verification, in which we reproduce the results of the paper as well as extend it to some other experimental setups. So a brief background, as now a lot of autonomous agents are being deployed in a lot of works. We need to verify that they're indeed aligned with what humans do want. So we investigate two different settings in which humans are aware of the reward function, but the robots may or may not be aware of the reward function. A brief mathematical background. So what do we mean when we say a policy pi dash is epsilon value aligned? It means that the difference between the value function of each state is bounded by the small number epsilon. And simply efficient value alignment verification means that we need to design a very small test, that is the number of questions on the test would be as minimized as possible, such that the probability of the agent passing the test is bounded by a very small number.
Okay, so what exactly is the notion of alignment here? One simple notion can be that the reward function that the agent has will be completely equal to that of the human. But can we just say that when the reward functions are not same, the agent is not aligned to human? Actually, the notion of alignment can be taken to comparing the policies. That is, if the policy of the agent is similar to that of human or is a subset of human's policy, then we can say that the agent is aligned to the human. We demonstrate this by giving a sample grid world example where we see that both the agents and humans policies are the same, but the rewards associated with each of the states are different. These rewards can be seen from table 1, where we just give the values of the rewards associated with each type of states in the grid world.
Coming to different algorithms and heuristics that the authors have used to do this verification. The main idea here is to use this aligned reward polytope, which is defined as this delta matrix, in which each row of this matrix denotes the difference between the feature count of two trajectories, one in which the very first action is the optimal one, and the second in which the very first action is suboptimal. The rest of the trajectory only takes optimal actions, and both the trajectories start with the same state S. Now, if W dash is the robot's weight vector, then if delta into W dash is greater than 0, then it means that the robot is aligned. This basically indicates that the robot is also preferring the first trajectory as the humans are also doing. So there are different query settings. That is, we can query directly the reward function weights. We can query the samples of reward function. We can also query the state value function and the state action value function. And we can also query the preference over different trajectories. Some other heuristics are also used. The first one is identifying critical states and then using these states in the verification process. Second is using the set cover optimal teaching algorithm to design trajectories and then asking these trajectories as question to the robot. And thirdly, instead of using entire trajectories, we can just use these single state actions as queries.
In order to validate the put forth claims in the paper, we mainly carry out 4 classes of experiments. The first class is to just validate whether the algorithms and heuristics work properly. So for this, we tabulate the accuracy, false positive rates, false negative rates, and the size of the questionnaire that is presented to the robot. And we indeed find that the accuracy for each of the algorithms and heuristics is quite high, whereas the false positive rates and false negative rates are low. We also validate our results with an extended action space. That is, we allow diagonal actions along with the 4 standard actions, that is up, down, left, and right. We also validate the results with nonlinear reward and state feature relationships. The claim put forth in the paper for the reward and state feature relationships in order to in order for an algorithm to work was that the relationship should be linear. So in order to uh, find whether this claim is correct or not, we try with 2 different types of relationships. One, we approximate the cubic relationship, that is x cube plus 10x, to be linear around the neighborhood of 0. And for nonlinearity, we completely shift to exponential function. Uh, as you can see from table 3, that The reward weight tester indeed performed poorly with nonlinear reward and state feature relationship, whereas the critical states tester has no impact of such change in the relationship. The fourth class of experiment was to try with critical states tester with a different threshold value. Threshold is simply what threshold is used for a state to be critical.
So, lastly, we would like to thank the authors because of the discussion that we had with them, which helped us to reproduce the results as well as implement the entire paper. Thank you.